This video is on the objective understand the properties of the chi-square distribution. Alright, so we're in chapter 11 here. We are introduced to a new kind of distribution. We've seen uniform distribution, binomial, back when we were talking about discrete random variables, right? Binomial distributions. Normal distribution, right? Standard normal. Student's t, right, which was pretty similar to normal, but had a certain, it was different for a different, number of degrees of freedom. And here we're introduced to a totally different, a totally new probability distribution. It's called the chi-square, and it's used in certain scenarios, right? And we're gonna talk about throughout these assignments related to the chi-square distribution. We're going to talk about in what scenarios does this distribution arise, for what kinds of tests. Right. So our first objective here is, again, understand the properties of the chi-square distribution. Now if you'd like to, see more about what they have to say on it, click on more instruction. Look at their videos, their notes, their examples. Hopefully those help you. And in fact, I'm going to show you some of their instruction here instead of writing it out, because it'll take a while to write out all this stuff. So here are the properties of the chi-square distribution. So have you ever wondered if lottery numbers were evenly distributed, or if some numbers occurred with a greater frequency? How about if the types of movies people preferred were different across different age groups? Well, we could answer these questions by conducting a hypothesis test, but not using a normal distribution. Okay. The chi-square distribution, right, pronounced chi-square as I've been saying it, is one that is used to determine the answers to such questions. Alright, so we're going to see there are three major applications of the chi-square distribution, right? Three scenarios in which this chi-square distribution will come up. So one is called the goodness of fit test, and there's actually a different assignment on each of these scenarios, right? Each of these types of tests where the chi-square distribution is occurring. Alright, so you'll be running a goodness of fit test, which determines if data fit a particular distribution. Alright, such as their lottery example, right? Say you were asking yourself, are the lottery numbers evenly distributed? Do they fit a uniform distribution? So if you're asking yourself, does a certain set of data fit a certain distribution? Is it uniform? Is it normal? Is it a student's t? Is it binomial? Is it whatever? You're going to run one of these goodness of fit tests in which a chi-square distribution will come up. Another scenario we'll come across, and we'll be running a test of independence, which will determine if events or variables, in most cases we're going to look at two variables, maybe height and weight or whatever. We're going to determine if these two variables or events are independent of one another. Such as in the movie example, right? Is the type of movie people prefer independent of age group? What age group they're in? Are those two independent variables? Or are they related in some way? Are they dependent? So we're going to run that kind of a test, right? A test for independence, and that test, this chi-square distribution will come up. And the final scenario, we're going to bring up the chi-square distribution, use it. The test for homogeneity, which can be used to draw a conclusion about whether two populations have the same distribution. Alright, so if you're asking the question, does this set of data, and this other set of data, do they come from populations that have the same distribution or not? And that'll be a test for homogeneity. And again, in all three of these scenarios, this chi-square distribution will come up. Alright, so the notation for the chi-square distribution is the following. So a variable x has a chi-square distribution, right? This symbol here that looks like an x over here with the square on it, this is the Greek letter chi, and it's chi-square with so many degrees of freedom, right? So kind of like the student's t distributions had so many degrees of freedom. Each of these chi-square distributions we come across will also have related to it a certain number of degrees of freedom that you're going to need to know. And where df equals degrees of freedom, which depends on how chi-square is being used. Alright, now they say here for chi-square probabilities we'll use degrees of freedom equals n minus 1. Ignore that because look at the sentence after this. However, the degrees of freedom for the three major uses are each calculated differently. Alright, so for the goodness of fit test, for the test of independence, and for this test for homogeneity, this number of degrees of freedom for our chi-square distribution will be calculated in different ways. Okay. The distribution is called chi-square because the random variable for a chi-square distribution with k degrees of freedom is the sum of k independent squared standard normal variables. So remember the standard normal z that had a mean of 0 and a standard deviation of 1. Well, imagine taking k independent variables that had standard normal distributions and squaring all their outputs and then adding those up. That gives us the chi-square distribution with, again, k, so many degrees of freedom, k degrees of freedom. There are an infinite amount of chi-square curves, right? Because there is a different chi-square curve for each value of the degrees of freedom. All right, and then here are some parameters of the chi-square distribution. The mean of a chi-square distribution is equal to the degrees of freedom. So mu equals, however many degrees of freedom. So mu equals k up here. The population standard deviation, sigma, is the square root of 2 times the number of degrees of freedom. So the square root of 2k in this example up top. The test statistic for any test is always greater than or equal to 0. All right. Because what you're going to see is, notice that, remember, it's chi squared. It's the sum of a bunch of squares of outputs, squares of standard normal variables. So when you look at the graph of a chi-square distribution, the number line, we're never going to look at negative values. It starts at 0 and goes to the right forever. So you know how like z-scores and t-scores, those could be positive or negative. For these chi-squared scores, they're always non-negative, always 0 or greater. Alright, so some properties of the chi-square distribution. The curve is always non-symmetrical. Alright, so again, very opposed to what we saw for students t or standard normal. Those were symmetrical and bell-shaped. That's not always the case for these chi-square distributions. They're always non-symmetrical and they're skewed to the right. Remember this, it's been a while, but skewed to the right means that the bulk of the data, the bulk of the height is on the left and it's got a long right tail. right? It goes off to the right forever. So you're seeing when the degrees of freedom is 2, it's this slopey thing here. High on the left, low right on a long right tail. And this goes to the right forever without ever hitting the axis. Kind of like your standard normal or student's t-curves. But it's bulky on the right. And then as you move to higher and higher positive values, the curve gets lower and lower. So it has a long right tail skewed to the right. And here's another example of a picture of a chi-square distribution where the degrees of freedom is 24. Again, getting bulbous on the left here, and longer right tail is skewed right. Now I'll say this: the higher the degrees of freedom gets, the closer to a symmetrical bell shape it looks. It looks close to a normal curve, not the standard normal, but it'll look closer and closer to a normal curve, a bell-shaped curve, the higher the degrees of freedom. Another property: a chi-squared curve starts at 0, as I mentioned, right? No negative values, right? It's a sum of squares of standard normals, so it's no negative values. Starts at 0 on the horizontal axis and extends to the right indefinitely. As it extends to the right, the curve approaches but never touches the horizontal axis. Again, as I mentioned, long right tails, skewed right. The population mean, mu, right, which is the number of degrees of freedom for these, is located just to the right of the peak. Just to the right of the peak. So here's mu here in this example. The peak is actually 2 less than that. The peak is usually at k minus 2, or the number of degrees of freedom minus 2, and that's the mode typically for a chi-square, but we're not going to need to know all that. And as with any other distribution, number 4, the total area under a chi-square curve is equal to 1, right? So from 0 to infinity, the area under the curve is 1, right? Just like for the standard normal, just like for a student's t, just like for any probability distribution, right? The total probability is 1. Right, and as I said this earlier too, right? As the degrees of freedom increases, the curves look increasingly like normal curves. Again, they get more and more bell-shaped. This is generally the case if the degrees of freedom is greater than 90. All right, so for example, if a variable had a chi-square distribution with 1,000 degrees of freedom, the mean would be 1,000, the number of degrees of freedom. The standard deviation would be the square root of 2,000, right? 2 times the degrees of freedom, or about 44.7, and the curve would be approximately normal, with mean 1,000 and standard deviation 44.7. And in fact, let me pull that up on the calculator. Right, so I'll pull up my TI-84 here, and I'll show you how to make a graph of a chi-square distribution if you need to. So I go to y equals, like any graph, y equals, and above the variables button were our distributions, and you see there's normal, right, t, students t, and you see number 7 here. There's number 7 and 8. There's chi-squared PDF and chi-squared CDF. If you want to actually now, if you want to find the area under these chi-squared curves, right, you go to chi-squared CDF, right? Just like the T-CDF and normal CDF for students T and standard normal. But if you want to make a graph of one, look at a picture of these chi-squared curves. I go to chi-squared PDF, and then for x value, just put x, and then degrees of freedom. And again, I'll put up the examples they've shown. If I just do 2 degrees of freedom here, right, that means the mean is going to be 2, and I'll just do this graph here. Alright, that's zooms, not zoom stat. Let me change the window up. So that means the mean is 2 and the standard deviation would be also 2 because it's the square root of 4. So x min at 0, right? Remember the horizontal axis will start at 0. I'll just have x max be 10 and y min be 0 and y max be 1, because really I don't think anything gets higher than, it's not going to be higher than 1 for the most part. See, and there's the chi-squared curve, and you see that back on the picture here, right? With 2 degrees of freedom, it's this kind of sloping down curve. And then I'll change it up. Y equals, let's just change this number of degrees of freedom to 24. And again, I'll change the window, because now the mean is going to be at 24. So I'll go out, and the standard deviation will be the square root of 48, which will be close to 7. So I'll go out to say 40. Yeah, let me lower the y coordinate. Alright, let me lower the y max to maybe a quarter. And there's your, see the chi-squared curve? Getting more bulbous, more bell-shaped a little. Now if I change it to 1,000 degrees of freedom like they're mentioning, they said, again, the higher the degrees of freedom, the closer to a normal, again, not the standard normal, but the closer to a normal distribution it'll get. And I'll change the window. Now like they said back on the page here, this should be approximately normal, with a mean of 1,000 and a standard deviation of 44.7. So let's say that's about 45. If I go like 2 standard deviations left, 2 standard deviations right, let's go 910 for the, let's go 900 for the x min and 1100 for the x max. Have the x scale just be 10 by 10s. And let's go like 0.1 there and see what we get. Yeah, I should lower my y. Let me zoom fit maybe. Go zoom and zoom fit, and it'll keep the x coordinates the way they are. And yeah, okay. So see there. It keeps my x, from 900. This is from 900 to 1100. But you see, it's much more bell-shaped, much closer to a normal distribution look, the higher the degrees of freedom. Alright, I'm just showing you, if you wanted to graph these on your calculator, these chi-square distributions, you can. You just need to know the number of degrees of freedom, that's all. Alright, so again, some key terms, right? Chi-square distribution, used to describe data and statistics that are positive and right-skewed. The chi-square distribution has one parameter, the number of degrees of freedom, right? Because once you know the degrees of freedom, you'll get the mean and the standard deviation. Right? The mean will be the number of degrees of freedom. The standard deviation is the square root of 2 times the number of degrees of freedom. Alright, then these are just some example questions. And then we'll get, when you see the chi-squared tables, there are going to be some problems where you have chi-squared tables. All the numbers on the tables are values that have a certain area to the right. So when you're seeing tables like this, these are critical values. So like, for instance here, if I was looking at a chi-square distribution with 6 degrees of freedom, the chi-squared value on the horizontal axis that has 10% to the right of it would be a chi-square value of 10.645. The value with 5% to the right would be 12.592. The value with 2.5% to the right would be 14.449, and so on. So all these values are just what's the value on the number line that has a certain area to the right. And we're only going to be talking about areas to the right for these because, again, there's no, I mean, you could talk about area to the left, right? The area to the left would just be 1 minus this, but, there's no left tail, right? It doesn't go on, it doesn't go beyond the value of 0, only non-negative values. So again, we'll get to some problems where these tables are. All right, so let's get back to the question. All right, so hopefully you watched through all that, and got a nice introduction to chi-square distributions there. So which of the following is a characteristic of a chi-square distribution? Select all correct answers. Well, it's skewed to the right. That is correct. Remember, it has that longer right tail. Symmetrical? No. Will not be symmetrical. So non-symmetrical, yes. And the total area under the chi-squared curves is equal to the degrees of freedom? No. Remember, total area under any probability density curve will be 1. So these are the only two that are actually, from what I was reading to you a second ago. Again, and read through the properties of a chi-square distribution. All right. So again, hopefully you paid attention here, took some notes or whatever, and even looked at it yourself. When you click on more instruction, and I'm hoping watching me do this and looking at your more instruction, reading the answer explanations when they come up, I'm hoping all this stuff helps you out when you're looking at this material and doing this stuff on your own. And thank you for watching.